Okay, so let's continue with questions on units and measurements, of which question one is saying, why is it important to always include the correct unit in medical prescriptions and the lab results? Why is it always, or why is it important to always include the correct unit in medical prescriptions and the lab results? So this question is more of requiring theory. I explained some of the importances of this topic when we started learning, and those are the things that you're supposed to bring in on question one. They just want us to show how important it is to show the correct units of measurement when you're talking about um, medical prescriptions and the lab results. So, one of the things or one of the points, I'm not going to mention all of them, I just mentioned two or three. This is question one. One of the most important reasons why we always have to label our or put the correct units when we are dealing with medical prescriptions and lab diagnosis, we have to ensure accuracy of dosage. Accuracy of dosage. So, why is dosage important? So, we have to show, if we're talking about drugs, for example, as me who is specializing in the field of pharmacy, if you're talking about a drug, you always have to indicate the correct units on a drug because what we know is that the purpose of administering a drug to a patient is because you want a certain pharmaceutical effect or a certain therapeutic effect. So if you don't include the correct unit on the dosage of your drug that is prescribed for a patient, you're going to find that there is going to be misinterpretation, and that can be also one of another point, but I've just included it into this same first point to say we have to ensure accuracy of dosage, of which it can also mean that we want to minimize minimize misinterpretation. Because if I give someone a drug and the drug is only written 5, you don't know what this 5 is because this is just showing us the magnitude and it isn't showing us the units of measurements that you are supposed to use. You don't, and the patient or the person that you prescribe that drug to might not know if this 5 means 5 grams or this 5 means 5 milligrams. And most of the drugs, to say a drug is meant to heal. It's meant to be therapy of certain conditions. But if you take those drugs in excess, they kill. They lead to abnormalities. You've heard to say someone drank 10 pills of Panadol and they collapsed. It's because those are toxic effects of drugs once you had an overdose. So if you didn't include the correct units of measurement on that prescription, we're going to find that just writing 5 is going to cause a lot of confusion. Billion times or billion mistakes can be made just by you putting this 5 because most drugs have a narrow therapeutic window. You're going to find that there is this graph, or let me just simplify it like this. You're going to find that if the dosage is low, it is not going to produce any effect. Then there is an optimum dosage here that can cause it, or that is going to result into the actual desired effect, the actual desired pharmaceutical effect of drug. Whilst if you put an overdose, it is going to lead to a toxic effect, which can lead to death and the many lots of complications. So we have to include the correct units. For example, most drugs are delivered in milligrams so that you avoid underdosing and also overdosing, hence ensuring that the dosage you've given is actually optimum for um, those particular characteristics or for the required effect. So I can just put these two as the reasons why you need the correct units when you're dealing with the medical prescription and also dosing. The other ones, you can look them up, but this is just theory and it shouldn't be something that gives you a lot of problems. So that was question 1. And question 2 is saying a, a, a defibrillator delivers 30 or 300 joules of energy. Express this in kilojoules. A defibrillator delivers 30 joules or 300 joules of energy. Express this in kilojoules. So this is question 2. This is question 2. And they are telling us to say this defibrillator delivers 300 joules of energy. 300 joules. And we want to convert this into kilo. I'm telling right here. We want to convert this into kilojoules. Kilojoules. So you know to say kilo when it means or when you're talking about kilo, that means you're talking about this guy 10 to the power 3 or 1,000. So how are you going to convert joules into kilojoules? It's actually by dividing this number of joules that you've been given by 10 to the power 3, of which this is the same as we're saying 3,000 or 300 divided by 10 to the power 3, which is just giving us 1,000. And this is actually going to give us our energy in joules, which will be equal to exactly 0.3 kilojoules. So if we convert our 300 joules into kilojoules, we're going to find exactly 0.3 kilojoules or 0.3 kJ like this. Hence, we've converted this guy from joules to kilojoules just by dividing by 1,000, because not to say kilo stands for 1,000. Okay, so that is question 2. Let's go to the next question. Question 3 is saying a patient's cholesterol is measured at 5.2 millimoles per liter. Convert this to milligrams per deciliter, given that 1 millimole is or 1 millimole per liter is equal to 38.67 milligrams per deciliter. A patient's cholesterol is measured at 5.2 millimoles per liter. Convert this to milligrams per deciliter, given that 1 millimole per liter is equal to 38.67 milligrams per deciliter. So here they've already given us the conversion factor, which means we don't even have to waste time on this question. It's as simple as it looks. So question 3. Question 3, we're supposed to convert the measured cholesterol, which is 5.2 millimoles per liter, millimoles per liter to milligrams per deciliter. Now they've already given us the conversion factor to say 1 millimole per liter is equal to what? Is equal to 38.67 milligrams per deciliter. So what are we going to do? We are going to multiply this number of millimoles that we are trying to convert by the conversion factor that they've given us, which means I'm going to say 5.2 millimoles per liter multiplied by this guy. The conversion factor, they've told us to say 1 millimole per liter is equal to 38.67 milligrams per deciliter. So I'm going to multiply directly with this conversion factor to say multiply by 38.67 milligrams per deciliter like this. So 5.2 multiplied by 38.7, this is giving me exactly 201.084 milligrams per deciliter. That is the answer that we are looking for. If we convert 5.2 millimoles per liter to milligrams per deciliter, we're going to get an answer which is equivalent to 2.0 or 201.084 milligrams per deciliter, and that is all on question 3. I move on to the next question, which is question 4. Question 4 is saying the heart rate is 78 beats per minute. How many beats is that in 5 minutes? The heart rate is 78 beats per minute. How many beats is that in 5 minutes? So this question is also simple and straightforward. Very simple and straightforward. Question 4, I guess. This is question 4. And they've told us to say if the heart rate is 78 beats per minute, how many beats are we going to have in 5 minutes? The question is as simple as that. What are we going to do? We're just going to multiply the number of beats per minute by the time that is elapsing, which is 5 minutes in this case. So I'm going to say my 78 beats per minute multiplied by 5 minutes. The minute and the minute here is going to cancel out. We have 78 beats multiplied by 5, and this is going to give us exactly 390 beats in 5 minutes. So that is the answer. We're just going to multiply directly since we know the conversion factor, or there is no even conversion factor. The conversion factor has already been provided to say we have 78 in 1 minute. How many are we going to have in 5 minutes? This question is phrased in such a manner that even in grade 5 or grade 4, even grade 1 should be able to answer. Okay, so that was all on question 5. Question 4. Let's now go to question 5. Question 5 is saying a doctor prescribes paracetamol for a child who weighs 18 kilograms. The recommended dose is 15 milligrams per kg of weight to be given every 6 hours. The available paracetamol syrup has a concentration of 250 milligrams per 5 mils. Question A. How many millimeters of paracetamol syrup should the nurse administer per dose? How many millimeters of paracetamol syrup should the nurse administer per dose? Question B. What will be the total dose in millimeters if the medication is given 4 times in a day? What will be the total dose in millimeters if the medication is given 4 times a day? Okay, so very interesting question. This is question 5, but also not a very confusing question. So this is 5. And in 5, they've told us to say the weight of the patient is 18 kilograms or 18 kgs. And the recommended dose, the ideal dose for the paracetamol syrup that should be given is 15 milligrams per kg. And that is every 6 hours. So 6 hours, you know, to say in a day there is 24 hours. That means if we divide our 24 hours in a day by 6 hours, automatically we are going to get the answer 4, which means this dose is supposed to be administered 4 times in a day. This dose is supposed to be administered 4 times in a day. So the concentration of the syrup that they've given is 250 milligrams per 5 mils of the syrup. So there's 200 milligrams of the paracetamol in 5 mils of the syrup, and we are giving this every after 6 hours. So the first thing was that we should do calculate the dose calculation per the dose per administration in mils. So how are we going to calculate the dosage per administration? Since they've already told us to say well, or the ideal dose is 15 milligrams per kg. We're just going to multiply this 15 milligrams per kg so that we get the concentration or the new concentration of the syrup that we're going to administer to this 18-year-old. So we're going to multiply this by what? By 18 kilograms. The kg and the kg here is going to cancel out. Did I say the kg and the kg? Yes, the kg and the kg. So this is mils or milligrams, not kg here. This is milligrams. So the kg and the kg is going to cancel out. That means if I multiply my 15 by 18, I'm going to get 270 milligrams per dose. So that means in those 6 doses that I'm going to give this 18-year-old, each of those doses is going to be having a concentration of 270 milligrams per dose. Now, they asked to say we should find this concentration in mils and not milligrams. So we're going to convert this 270 milligrams per dose into mils using the concentration of the syrup, of which, where is the concentration of the syrup? It is this guy that they've given us here to say the actual concentration of the syrup is 250 milligrams per 5 mils of the syrup. Now we're just going to use a simple ratio and proportion here to find the concentration in milligrams. What are we going to do? We're going to say since there is 250 milligrams in 5 mils, how many mils, of which I'll put X here, are we going to have in 270 milligrams? 270 is the actual dosage that is going to be given to the 18-year-old. So we can just cross multiply here, such that we are going to find X, which is the concentration in mils, to be equal to what? To be equal to 270 milligrams multiplied by 5 mils divided by 250 milligrams, like this. So the milligrams here and the milligrams there are going to cancel out, and we are going to remain with our X, which is the actual concentration in mils, to be equal to 5.4 mils. So that means the actual dosage that you are going to give in mils should be 5.4 mils per dose. I hope there is no question there. That is question 4. And after this, question B is saying we should calculate the total dose. What is the question? Question is saying we should calculate what will be the total dose in millimeters if the medication is given 4 times a day. So we've already done the work in part A, that's that in part B. The only thing we're going to do is calculate or is multiply this 5.4 mils per dose multiplied by the number of times that we're going to give this dose, of which you said since it's given after 6 hours, it is going to be given at a total number of 4 times in 24 hours or in a day. So I'm going to say this multiplied by 4, which is going to give me an answer of 21.6 mils per day. So that means the total dose in a day in mils is going to be equal to 21.6 mils in a day. Okay, so that was all on question 5. We can now move on to question 6. Question 6 is saying if x is equal to a plus bt plus ct squared, where x is in meters and t is in seconds, what is the unit of c? If x is equal to a plus bt plus ct squared, where x is in meters and t is in seconds, what is the unit of c? So we're trying to find the units of c, and we can see to say c there is just a constant. So here is a crack. When you are given such questions and they want you to find anything, be it units or the powers of anything that is on the right, what you're supposed to know is that if an equation or everything on the left hand side is, or everything on the right hand side rather, is equating to x on the left hand side, what does that mean? That means all the terms must have the same units as x. All the terms that are on the right are expected to have the same units as x. And how many terms do we have on the right? We have 3 terms. We have a, we have bt, and we have ct squared. So these are the 3 terms. And what are we learning from this graph is that all the terms must have the same units as x. So this is question 6. Question 6, and we've been given to say x is equal to a plus bt plus ct squared. And they've told us to say x is in meters. X is in meters and t is in seconds, s. So since we have 3 terms on the left hand, on the right hand side, which is a plus bt, these are not like that. We have a and bt and also ct squared. That means how are we going to relate these terms to the left hand side, which is having x? We're going to say x should be equal to what? Should be equal to a. X should be equal to bt, and x should be equal to what? Should be equal to ct squared, like this. That's how our equation should be. And they've told us to say t is in seconds whilst x is in meters. So what are we supposed to do here? We're only going to replace the units that we already know into this equation for c. Since we want to find the units for c, let's just concentrate on c here. So let me do this. If I want, I can just say since this is m, that means also on the right hand side there should be m. So that means the units for a are in meters. X is equal to bt. You know, to say on the right hand side we have m, whilst on the left hand side we have b and a second. That means the actual units for b are going to be equal to what? They're going to be equal to meter per second. On c, we know to say we have m for x on the left hand side. This will be equal to what? It will be equal to c multiplied by t squared, which just means second squared. That means I'll divide both sides by second squared so that I remain with c here. That means the units, the actual units for c are going to be equal to what? C is going to be equal to meter per second squared. And that's that. We've related everything. We've related a to m, bt to m, and ct squared to m, of which m here is just representing x, which is on the left hand side. So the actual units for c here, since they only asked for c, we're going to say c is equal to meters per second squared, just like that. And we've answered question 6. That is all on question 6. Question 7 is saying the volume of a liquid flowing out per second of a pipe of length L and radius R is written by a student as V. to be equal to pi PR to the power 4 over 8 and L. V is equal to pi multiplied by PR to the power 4 over 8 and L, where P is the pressure difference between the two ends of the pipe. Then we have the coefficient of viscosity. And what else? Prove that the equation is dimensionally consistent. Prove that the equation is dimensionally consistent. So this is a very interesting question, which is talking about dimensional analysis. And I'm going to go to my blackboard. This is question 7. So on question 7, what are they asking from us? They just want us to prove that this equation, which is V being equal to pi P R to the power 4 over 8, the coefficient of viscosity L is dimensionally consistent. So how do we check if an equation is dimensionally consistent? We are going to check the dimensions on the left-hand side, which is this guy, left-hand side, and also check the dimensions on the right-hand side. So if we find that this equation is dimensionally consistent, that means the dimensions on the left-hand side should be equal to the dimensions on the right-hand side. If not, that means this equation is dimensionally inconsistent. Hence, we can conclude that it is also dimensionally incorrect. So let's do that. So we've been given volume on the left-hand side, and you know to say the volume. Okay, so this is not just volume. Sorry, this is a volume flow rate. Where is it? Flowing out per second. So V is showing us volume flow rate. Then they've told us to say L is length pi, and R is also radius. So those two guys should be having the same dimensions there. So V, since it's volume flow rate, we know to say the SI unit for volume, we can use cubic meters, or sometimes we can use liters. So since it's volume flow rate, that means it's volume per rate. Since it's rate, you know, so we're dealing with it at a time. How much time is taking for a certain amount of volume to flow in this pipe. So this is volume flow rate, that means it's going to have units of cubic meters per second, since second is the SI unit for time, or we're going to say liters per second. As simple as that. So I'm going to use units here, which are these guys. I would prefer use the cubic meters per second so that we're not confused everywhere going. So that means we've concluded on the left-hand side, we're having dimensions of cubic meters per second. So now what are we going to do to the rest of these things? They've given us pi in the formula, and we know to say pi is dimensionless. Why? It's because pi is a dimensionless constant. So this guy doesn't have dimensions. They've given us P, which is pressure in this case. And you know to say pressure as units of force per unit area. We've been talking about this. Oh, sorry, it was the second semester, guys, not you. Pressure is equal to force per unit area. So this is going to lead into what? Force has SI units of newtons, whilst area has SI units of what? Meter squared. And force or newton can also equate to what? It is equal to kg meter per second. So that means the SI or the SI units or the dimensional units for pressure are going to be finalized as kg meter per second, like this, over meter squared, like this. These are going to be the dimensions for pressure. Sorry, this is per second squared. The dimensions for pressure are going to be these ones, but since we have m down here and m as a numerator, we're going to cancel this guy even in there, such that we are going to remain with the 1m down there on the denominator, which means everything on pressure, the dimensional units for pressure are going to be equal to kg. Then we have a numerator or a denominator m, giving us m to the power minus 1. Then we have time or per second squared here. So we're going to multiply this by second to the power minus 2. So to save some space, I'll just write it here. I just wanted to show you how we are coming up with the actual dimensions for pressure. Okay, like this. Just write them here to say for pressure of kg meter per second squared, like that. Okay, then what else do we have? We have coefficient of viscosity. So the coefficient of viscosity is going to have units of what? Of uh or how can I put it? I can say pascals multiplied by second. And how is that actually relating to the actual units that we know? It is just going to give us kg meter second, the power minus 1, like this. Then you have length, of which you know to say length is having dimensional units of L. Even R also its radius. So it's going to have the units of M. Let me rub here. R is going to have the dimensional units of M. Now we can plug these guys into the formula that we've been given so that we can find the actual dimensions on the right hand side. So we've said the pi that is here is dimensionless. So we're going to ignore this guy, since in dimension analysis we're only focusing on the things that have dimensions other than constant. So even the 8 that is on the denominator is going to cancel out. So that means on the left hand side, what do we have? I have pressure, which pressure has dimensions, kg meter to the power minus 1, second to the power minus 2, multiplied by r to the power 4. So I'm multiplying this by meter to the power 4, since r is equal to meter. And that divided by the coefficient of viscosity, which is kg meter to the power minus 1, second to the power also to the power minus 1, multiplied by length, which is just m here. So we can see that some things can already cancel out. We have kg down here and kg on top, which means these two guys can actually cancel out. What else do we have? We have m. We have m to the power minus 1. Let me check again. Okay, we have m to the power minus 1 down here, and also m to the power minus 1 at the top. So this m, before I cancel it out, or I can just cancel it out just like this, because if I cancel this m to the power minus 1 out, I'm also going to cancel out this m to the power minus 1. That means at the top, what am I remaining with? I'm remaining with the second to the power 2 multiplied by meter to the power 4, this divided by second to the power 1 divided by this guy m. So m can cancel out with 1m here, such that I'm going to remain with 3 there. Then I have m to the power minus 1 here. This can cancel out with also one of these, such that I remain with s to the power this. I remain with one of those there, which means what am I going to remain with? I'm going to remain with this m to the power 3 as a numerator, m to the power 3. And what else? I'm remaining with this second to the power minus 1. All the things that are remaining on the numerator. So I'm going to remain with m to the power 3 multiplied by second to the power minus 1 like this. So you can see to say these guys that we found here on the right hand side are the same with the dimensions that we found on the left hand side. Hence, we can conclude that our equation is dimensionally consistent, because what are we remaining with? We're remaining with these guys that I've left on the bottom there. And these guys are exactly the dimensions that we had found on the left hand side. We said on the left hand side we have cubic meters per second like this, or liter per second. So I said I'm going to use this, hence we're going to compare this on the right hand side, m to the power 3 over second. This is exactly equal to this that we found on the right hand side, which is also m to the power 3 over second like this, which means our equation is dimensionally consistent. And that is all on question 7.